Hello student, this is my 7th lecture on real analysis. I am Ms. RANJANA DUTTA from the Department of Mathematics, the Graduate School for Women. This is for 3rd SEM Honors and GE students. Now, we will discuss today also some more examples on continuity and differentiability. Example: prove that the function fx is equal to modulus of x is continuous at x equal to 0 but not differentiable at x equal to 0. So for continuity we have to check the left hand limit, the right hand limit and the central limit at x equal to 0. For that we'll write f0 plus 0, f0 minus 0 and f0, and which when the function is fx equal to modulus of x, when you put this on this we get the left hand limit, right hand limit and the central limit all are equal to 0. Hence the function fx is continuous at x equal to 0. Now for the differentiability we find right hand r f dash 0. So which can be written as limit x tends to 0 f0 plus h minus f0 by h, which gives us 1. So right hand differentiable is equal to 1 and left hand L f dash 0 is equal to minus 1. Since the right hand limit differentiation is not equal to the left hand differentiation, hence the function fx is not differentiable at x equal to 0. Here, take another example. Discuss the continuity and differentiability of the following function at x equal to 0. And fx is equal to 2 plus x if x is greater than or equal to 0. See here, x is greater than or equal to 0 and 2 minus x if x is less than equal to 0. So for continuity, we find f0 is equal to 2. For f0 plus 0, that means more than 0, then the first 2 plus x should be taken. That is 2 plus x, and here x is equal to 0. So here f0 is 2, f0 plus 0 is 2 and f0 minus 0 is also equal to 2. So 0 minus, when the function is 0 minus 0, then we have to take the function fx is equal to 2 minus x and put x is equal to 0 in the formula for continuity of the function. So we get f0 is 2, f2 plus h is equal to 0 plus 0 is 2 and f0 minus 0 is also 2. Hence the function is continuous at the point x is equal to 0. Here, see, in the case of when x equal to 0, we take the fx for 2 plus x. When x is less than equal to 0, we take fx as 2 minus x. Now, for the differentiability, right hand side, f 0 plus h minus f0 by h. So we write limit x tends to 0 fh minus f0 by h. So f h and h is greater than 0. So take the first function, that is 2 plus h, and then calculating we get x, right hand limit is equal to 1. Similarly for the left hand limit, f minus h minus f0 minus divided by minus h, we get the value is equal to minus 1. Since the right hand limit is not equal to the left hand limit, hence the function is not differentiable at x equal to 0, not differentiable at x equal to 0. Now, next question given on your screen. Please try it at home. Next, discuss the continuity and differentiability of the function fx is equal to 1 by x when x is not equal to 0 and 0 when x is equal to 0. Then f x plus h, f alpha plus h minus f alpha can be written as 1 by, in place of x we write it as alpha plus h minus f alpha 1 by alpha. Then after calculating we get minus h by alpha into alpha minus h. So when h tends to 0, f alpha plus h minus f alpha becomes 0. So fx is continuous at x equal to alpha. Again, for differentiability, f alpha plus h minus f alpha by h, then substituting the values in, we get, and after putting h is equal to 0 we get minus 1 by alpha square. Hence fx is differentiable at x equal to alpha. So the function is continuous at the value of x is equal to 0. So the function is continuous at the value x equal to 0. For this, 0 plus h minus f0 can be written as modulus of 1 by h minus 0, that is 1 by 0. This implies that fh minus f0 is equal to infinity. Hence, fx is continuous at x equal to 0. Consequently, fx is not differentiable at x equal to 0. Now, consider a function defined by fx is equal to x for x lies between 0 and 1, and when x lies between 1 and 2 is equal to 2 minus x, and when x is greater than 2 it is x minus 1 by x square. For continuity at x equal to 1, we check f1 minus h, f1 and f1 plus h. F, when it is function is f1 minus h, that is fx is less than 1, so we take the first value, that is x, and here it is f1 minus h can be written as 1 minus h, and after putting the values of h we write it as 1. Next, f1, f1, the second x lies between plus 1 and 1 and 2, we take the second value, and it is 2 minus x, that is 2 minus x is here 1, so 2 minus 1 is 1. And for the third, x is greater than 1. X is greater than 1 means x is greater than 2. X is greater than 1 means we can write the second value also, we can take the second value or the third value, both. And after substituting these values, we can find that its value comes out to be 1. So, hence we can find that when x is equal to 1, the function is continuous at the point x is equal to 1. Similarly, we can show that if x is continuous at the point x equal to 2. Now, for differentiability, we find right hand differentiability, that is R f dash 1 and f1 plus h. f1 plus h can be written as 2 minus h and minus f1, and after putting these values we get right hand limit is not equal to left hand limit, hence the function is not differentiable at the point x is equal to 1. Again, for the differentiability, to check the differentiability at r f dash 2. So here r f dash should right hand side f dash 2, that is when x is greater than 2 plus h means when h is greater than 2, we have to take the third function as fx, and then substituting these values, that is 2 plus x minus half x square. So in case of x we write f 2 plus 2 plus h minus half 2 plus h the whole square, and so on, we get that is equal to minus 1. Similarly, left hand f dash 2, here 2 minus h, that is the value is something less than 2. So then the second function 2 minus x has to be taken, and after calculating it we get it is also minus 1. Since the right hand limit is equal to the left hand limit at the value x equal to 2, hence the function is differentiable at the point x equal to 2. So today this much only, you try at home and do the homework as given. Thank you.